this T, Ct becomes a composition operator if and only if this ut. This ut is the random Nicotin derivative of mu t inverse with respect to mu. Because your mu t inverse, that is measure of the t inverse of A, that comes out to be measure whenever your t is a measure. So with that measure and non-singularity says that measure of t inverse is less than or equal to the random Nicotin states, you can find a locally integrable functions, and that is denoted by ut. So if my ut comes out to be here, then this. And this result state now again, if I take my this equality also here, if I p equal to q, then I get my non-singular t is non-singular measure, then my
lost track of non-singularity transformation. What is that?
with non-singular definition.
What's that?
It is measure of the t inverse of A has to be 0 whenever measure of A is. That A is on that side and then 0. So if T is a non-singular mapping and my P is equal to Q, then this result comes out to be this composition operator Ct becomes a continuous and bounded mapping on LP spaces. And this condition comes out to simply, I can replace this one by mu T inverse of A. Yeah, I can just simply mu T inverse of A is less than equals to B time measure of A for all A belongs to that correspond. If it is my Ct is from LP to LP. If and only if, I mean that is, once I write this, I mean the boundedness, it is continuous and well defined. If and only if my T is taken to be non-singular. It is non-singular. If T is non-singular, then this mapping becomes continuous if and only if this condition holds for every A in the sigma algebra, whichever notion I am using for that. So if this for some B greater than 0. If this is so it comes from this result. And now this is a challenge to characterize the boundedness of composition operator on variant exponentially big spaces. Nothing has been done. No study has been done about the composition operator and weighted composition operator about this. We initiated the study with the Alberto Fiorenza. But still we are failed to find a good characterization, efficient conditions, and the result that we have obtained in this way, I will come to that. Recent, and we have got in the partial other way, sufficient as well as some necessary condition, but we have failed to get this characterization. Some good characterization, although what we have got, that was a very little less and very weak result, I will say. Although it's a paper of 24. Then I'm able to get to conclusion.
Also, a conjecture.
It is not very good.
It's not equivalent.
No, that is not. It is not factorizing.
No, I am saying it doesn't look like they'll be equivalent.
Which would equivalent to?
The
equivalent to continuity of this. Yeah. That is what I'm saying. It is one way result of it is not equivalent.
Then I am saying it's a conjecture that it won't be equivalent.
No, I don't have any conjecture on that direction because we don't have so much ideas that we can even give that it will be a conjecture on that.
It's much simpler, I guess.
No, it is not. It is simpler in one sense because in Alberto Fiorenza got one thing. But still, it's a challenge to get the better result on this direction. Similarly, we have another paper that is studying vector composition operator on these spaces. Although we have done compactness of this study, essential range, and some properties have been discussed and certain result has been obtained, but very less I told you. We have obtained about these spaces. That's what from this, and we have the direction on our paper, and this is the paper which we have got with the Alberto, this one, and that's all from my side. Thanks to you for the questions for hearing. Thank you very much.
So this is what I mean. I thought, is it NL map?
Yeah, and also.
I know. Because there are advances in operator too.
Analysis method का sir.
अच्छा,
Analysis method.
Okay.
It is in there.
अच्छा, एक बार, have you tried compact groups, for example, in place of X, Y? There's a R major sitting over there. Has it been?
Actually, I don't think it's right. As per my limited knowledge, we are going to the linear structure. It might be we haven't gone on group study structures because if you just find the study of composition of them is going to three directions. One is when the study is confined over the miserable sets and all that, and the another one is when they are talking to the holomorphic T is taken to be the.
No, but then you can't talk of measurability in case of compact groups.
We need to have the measure over here, but
You already have it.
yeah, that is the composition operator study over here, but we haven't gone on that.
Thank you.
Thank you very much, sir.
In fact, we have completed within this time, and I would request the future persons to deliver it as he suggested. Within that, and that starts with me.
Thank you. Charity begins at
Doesn't
home.
end with me.
तो पहले करते हैं इसको बिगड़ जाओ.
So, are we starting now?
Yeah.
Yeah, sure. आप बोर्ड इस्तेमाल कर
नहीं, someone can help me out with this. Anyone is here? Because-
You are Yeah, it's my great pleasure to introduce our friend APC. We usually meet in conferences, and that's a good time. We look forward to meeting each other. I'm happy to introduce him, and he'll be talking about on Bunge sets of transcendental entire functions. So we'll start at 4:35. So
Okay, thank you very much. The topic, as you can see, is complex dynamics and Bunge sets of transcendental entire functions. Basically, complex dynamics is iteration of a function, there is a applying function again and again in terms of composition. Now, for all practical purposes, there are 4 different categories that we work on. That is the rational functions. Examples are there. Rational entire function like sin z, cosine z, where Morpheus functions which has an omitted value like e raised to z by z, or maybe something like tan z, where we have more than one pole, maybe 2 or 3 are entirely made. The reason is that the proof many times, of course, the result may be the same. Of course, many times it's different. Sometimes the result is the same, but then the procedure may be different. So something is true for one property, one category, it may not be true for the second. If it is, then the things have to be done in a different way. So for that we have this, and my concentration here will be basically the second one, but with a little understanding of your first one. We start with the following, that f be a rational function, then of course this is our usual notation, f naught of z is z and fn of z is f of z, applying f again and again n times, that's your fn of z. Let's take the first example, consider if z is equal to z square, then observe that if the value of z is less than 1, say for example it's half, iterations will be half square becomes 4, 1 by 4 and so on. So the points are ultimately will converge to 0. So everything from here converges to 0. The quantities here will tend to infinity. For example, 4 becomes 4 square 16, that goes on this side. And similarly, the other points also go to infinity. So we have a point, the convergence here and a convergence here. And the quantity on this circle, if it has a rotation, I will not go into details, if it has an irrational rotation, type of rotation, it will keep on rotating again and again and again. But if it's a rational type, maybe ultimately we come to 2 pi, e raised to 2 pi is 1 and then 1 remains 1 square, 1 square, 1 itself. So the quantities here, they may converge or may not converge. So it divides into 2 parts, that is Fatu, this part where convergence, that's Fatu, the other is also Fatu component, and here is your Julia set. So now here observe, the complex plane has been divided into 2 parts. That is the only thing I'm saying here. The complex plane has been divided into 2 parts, the Fatu portion and the Julia portion. The question, of course, is, this was the example that we took here. I take another one. This one, 1 by z square. Again, in this case, the quantities, they will keep on going, say 1 by half. Half will go to 1 square, will give you 4. That comes to 1 by 16. And then 16 square, and so on. It keeps going this way and this way. But a subsequence is converging here to 0. And a subsequence is converging here. And that's your normal family that we talk about. And that again gives you the Fatus component and the Julia set. The same thing is there. That is even for f z is equal to z square. But there is a fundamental difference between these two. In the first one, the points converged. Here also converged. But here, if you observe, in this case, the point from here, it moves up here, then comes up here, and then comes out, and keeps on going this way, zigzag. So now, if it does this zigzag, we call it as a Bungee set. Bungee set also, जैसे circus में होता है, it goes up and down, up and down. The same thing is happening here. It's called the Bungee set. No doubt the answer is the same. But now we have a different category, that is the Bungee set. And so now the complex plane, and of course, the way we define it, because of the shortest time, I'll just skip a few things. So of course, this is a Julia set that we have. Maybe I may come back to it a little later. Yes. For a transcendental function, this is how we define. There are 2 things that we have. One is called as the quantities which converge tend to infinity, and a quantity which are bounded. And then there are quantities, as we just saw in your Bungee set that we had there, neither bounded nor unbounded. 1 second. It hasn't been ringing for the last 48 hours.
Or Murphy's law.
Let's do it.
1 second. 1 second. So I think now we can go in a reverse way. So we have these terms. These are the quantities which are bounded. These are the quantities which are tending to infinity. But a quantity which is neither bounded nor unbounded, that is called as a Bungee set. And so in that case, what can we expect? One thing is that in the sequence that we are having, there are some points which tend to infinity, and there are some points which come back. So neither converging nor diverging, you can call it. So those are the Bungee sets. So now we have a complex plane divided into 3 parts. Earlier it was only 2 parts. Now the complex plane is divided into 3 parts. And interestingly, there are some points of this Bungee set which are in the Fatou set. There are some points of the Bungee set which are in the Julia set. So it means now we have a different type of structure coming up. And this work has started hardly maybe 7-8 years back. Earlier it was only Julia set and Fatou set, but now the Bungee set has also come into picture. Now this is the background that we are having.
But Julia and Fatou are disjoint.
Yeah, Julia and Fatou are disjoint, and this is overlap with quantity. They are completely invariant. Fatou set and Julia set are completely invariant, and consequently,
What does it mean? Completely invariant?
that means if I take a point on a Julia set, the forward and the backward, they remain in the Julia set. Similarly with the Fatou set.
But not.
And नहीं, इसके अंदर भी जो आएगा, then will be completely invariant. The reason will be that if the quantity is tending to infinity,
Between two sets.
the quantity that is tending to infinity, every point naturally that we are moving, the point here is tending to infinity. The next point is also tending to infinity. The previous one is again tending to infinity.
So
So
it's
it's not really
separately
invariant.
invariant. Separately invariant.
Separately invariant.
Two components.
And the other is bounded. So if it is bounded, the previous portion is also bounded, and so on. And this is the complement of these two. So it is the Bungee set. So any point that I take of Bungee set, it will keep going up and down. So it's completely invariant. So they are completely invariant.
The name is after some mathematician, right?
Which are Bungee?
The
No,
Fatou and Julia are, but Bungee is because of the Bungee.
Bungee वो
Bungee jumping.
सर्कस नहीं सर्कस में जो कुत्ते रहते हैं ना वो उसके अंदर नेट के अंदर ऊपर नीचे आके रखते हैं. So from that point of view, that's only Bungee set.
In India, you don't have anybody's name as Bungi, but I thought it was.
So this is the background. So now I think I'll go a little slow, so that at least. Yeah. So this is what we had started with. And here, of course, if you observe the Julia set is just a circle, but in general, it will not be a circle. The Julia set can be very complicated, and many of you may be already knowing it, so I'll not go into it. So you can just see the Julia set is complicated, and interesting part is that the interior of the Julia set is empty. So that means the Julia set doesn't have any thickness. Just as we saw in that circle, there is no thickness. Similarly, here also you can see there is no thickness. It's only those lines. So it can be bounded or it can be unbounded and completely invariant. That's the point. If I take from Julia set, the forward will be again on the Julia set, the backward point will be always in the Julia set, and so on.
Will it be a measurable set for my own interest?
May be, I don't know. I have no idea.
I will have then another example of
Okay.
one set
Yeah.
example.
You can try. You can try it. Okay. So it is Julia set is empty. So we have this situation. It's a completely invariant. So if you look at the components, the middle portion, for example, that is part of the Fatou set. Now, once I apply, so Julia set is going to be roughly the lines or the diagram, but no thickness. So this part is a Julia set. So that they are complement. So these are the Fatou components. Now when I apply the function, so the image of this has to be somewhere. The image of this cannot be a part of it. For example, if it's this part, then a part of the boundary comes up somewhere here, which is not allowed. It's a completely invariant. The boundary should go to the boundary. So the image of this is going to be the whole of it. The image of that is going to be the whole of the next one or wherever it is. So if it keeps going like this, it is called a wandering domain. It keeps wandering from here and so on. And if it comes back, it's called the periodic domain. So that is your periodic domain. In this case, it's the period 3, here, 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 and then back here. And it cannot be a part of it. Naturally, the blue cannot cross the blank portion. So it has to be of this form. Now, once we have this, the other thing that came into mind was 1920s, more than 100 years back, was that Julia studied this quantity, the function z plus 1 or e raised to z, and he observed that there are points which tend to infinity. Observe that for just a simple example, if I take z as 1, so it is back to 2 plus something, 2 would go to 3 plus something, or it would tend to infinity. Similarly, everything happens to many of them, and he asked whether this is always true. And this was studied by Eremenko. He defined I of m and said for that so that the nth iteration tends to infinity, and he called it as the escaping set. Now, the moment it's escaping to infinity, he proved some result, and he stated that I bar has no bounded component. Of course, there are other properties, and he conjectured that the bar can be removed, that IF has no bounded component. And a lot of work on, because he conjectured it, the whole theory started working on the mathematicians started working in this particular direction. Now, before I go further, let me just point out one thing here. Look at this for Julia set of F. It was the sequence converging. Converging was your Fatou, non-converging was your Julia. So it was in terms of convergence. Here you observe it is the boundary of the points escaping to infinity. That means the Julia set can be studied using points we are tending to infinity. If the points are tending to infinity, the boundary that I get is going to the Julia set. So the convergence comes up in this way also. And people have started working. And because of that word, and because of this conjecture, people started working in this direction. Now, if the quantity is tending to infinity, if you want to work, what happens? You start looking at, does it converge to infinity at a slow rate? Or does it converge to infinity at a fast rate? So what would happen if something is converging slow rate, and what would happen if the quantity is converging to a fast rate? Now, this slow and fast has to be mathematically defined. And this was done by many mathematicians, and then results were obtained. So this was one of the way of defining convergence tending to infinity. Where if you observe, this ratio should tend to infinity. Geometrically look at it, what it says. It says n plus 1 iterate and nth iterate. So nth iterate and n plus 1 state, the cap. That quantity should be large. Only then it tends to infinity. It's like saying 100, the top one, the next is 10 down, cancellation comes out to be 10. In the next stage, it is 200 divided by some 50, something, and so on. So, as long as the caps become larger and larger, the caps become larger and larger, it is tending, and results were obtained.
Why do we have to take log?
to reduce down the speed, otherwise it becomes difficult to analyze the things. Because both will be tending to infinity. If two quantities are already tending to infinity, then trying to measure them, you would require, it's like saying, say, 2x and x. If you're talking, no, let's say x squared and this portion, both are tending to infinity. And this also x squared and no, let's take it this way. I'll log of x. I'll come back to it. Say log of x squared and log of x. So now, of course, both are tending to infinity. And if I want to compare them, had I taken, if I take the log of this, would give you 2 times log x, and here would be log of x. So you get ultimately 2. If I take log of both the quantities, log of x square would be the corresponding quantity comes up here. So you will be getting something.
Stay inside the log. Without putting log, either ऊपर कर दीजिए.
Log x square. So it will be giving us, but this portion was tending to infinity, this portion was also tending to infinity, and then comparison would be not possible. But taking a log would give you 2 times log x, and here log x only. That means this is growing at a faster rate. So faster than this quantity. So you require log. Yeah.
Instead of changing, can we change this law by some other function, so that the, or is the notion of faster depending on this function?
No. No, it doesn't depend upon only log. It can be changed. That's there. It can be changed. Yeah. But basically, if you remember, when we are talking about the order of an entire function, we use log MRF over log of R. That we are trying to compare with e raised to R with the R, and there we use it. So this comes from there. And this is one way, and let's observe, there are other ways, it's not only one way. Now look at this one. This is another one that has been taken. Log of x over log of x. This time it's not the gap, it is the iteration. So log, because the reason I will just you here is normally when you are talking about transcendental entire function, they grow at a very fast rate. E raised to. So to compare that, we have to take some logs to bring it down. So here is another one, and they have used it, and there are other ways also in which it has been used. So I'm not going into those details because I think how much time is it still left?
About 20 minutes, so 10 more minutes.
10 minutes, okay, yeah. I'll keep that in time because I've already told that I have to complete business.
Sure.
Okay.
10 more minutes.
So this is another way. Now, if something is tending to infinity, and people have worked on it, and the boundary of the converging gives us idea of the area. So why not work with that? So people work with this, and a lot of work was done in this. Okay. And in this also, many results were obtained. I'll skip all this. And this was a conjecture. No. Yeah, this was the conjecture that was mentioned while the constitution to infinity. In this, he conjectured in 1989 that IF has no bounded components. And this conjecture was open, and people started working with it, as I mentioned, with different speeds, and people thought, well, it may be true. And it's only just 2 years back, it has been disproved. And also, the proof has still not come, it's only in the math archive. So officially, it is still not out, but it is there in my archive that this conjecture is false. That there is an example where this does not hold. Yeah, this is counter example in April 24. Counter example to Ehrmann-Cruz conjecture that X is a subset of C be non-empty, full and connected compact set. That it should be compact and full. Full means the whole piece. Compact set is this type, not of this type. So closed and bounded can be of this type also, but not of this type. It has to be full.
What is the technical definition
But yeah,
of full? Yes, an interior point?
there's
Whether that
no, there is the complement. If I take a complement, is simply connected.
Complement.
Complement of this portion is simply connected. Here it is not.
It's not full and whatever is the
Yeah.
here it is.
Yeah.
It's not full.
So it is full if its complement is.
Simply connected.
Simply connected. Yeah. So this is the result. Let X a subset of be a non-empty, full and connected compact set. Then there exists a transfer entire function F so that X is connected component of F. So there is one with this. And again observe, it just uses the word there exists. So a lot of work, which one? No one knows. It is there, existence is there.
Choice Muski.
So it exists. But which one? It's like saying that something is tending in this direction, something is tending in this direction, then there should be a point which is moving either in this direction or in that direction. Which is that point? Is it 3 or is it 4 or what? We don't know. It's like that. So this is the existence theorem that we have.
So
And-
then, seriously, does he use action of choice?
No. It's a rational approximation. He constructs a region, and for that, it's a continuous function, then under that, there should be an entire function having those properties. So that point of view, approximation. Rational approximation. So now, the other is this set. We're talking about tangent to infinity. Now here are the points. A of f is set of all z so that there exists an R so that fn of z is less than equal to R for n less than equal to 0. For n greater than equal to 0. That means everything is bounded. So quantity, if it remains bounded, is denoted by k of n. It's like saying, if I take a point here, it moves up here, it moves up here, it moves up here, but never goes out. So that's your k of n. And the Bungee set now is the complement of this type of a situation and that type of a situation, that's your Bungee set. So for non-linear polynomials here, this is called as the Fielding-Julia set. It has been extensively studied, and here has been studied by, this is a recent work, the term Bungee set came up in 2012 and 2013. That's when the work started. So Bungee set of F is C complex plane minus the points which are tending to infinity union the bounded portion. So none of those is your Bungee set. And for a polynomial, Bungee set is going to be an empty set because everything will converge to infinity, so no boundedness number. For a transentire function, Bungee set is known to be non-empty. There are results for that. In fact, for a transentire function, Bungee set of F, intersection JF is non-empty. That means in the Bungee set is the point of the Julia set and vice versa. There are examples where for two set intersection Bungee set is non-empty. In fact, if you observe this result we had f z equal to 1 by z square, all these points, because this point went here and then came back and then went out and so on. Remember, this is not the oscillation. In oscillation, there is a fixed distance. It comes here and here. Here it is different. It keeps within this region, and at the same time, the next position is going to be somewhere here. The next position will be here. It will not just, because the moment it is just bounded, oscillation will just put everything in bound. So it cannot be an oscillation. It is a bound set. It keeps increasing as well as decreasing.
How about those functions which are periodic, let's say?
No, if they are periodic, they will not. It depends upon the type of function that you are having. If because when you are talking about complex analysis, complex dynamics, there are 4 or 5 different types, and all of them are periodic. The moment they are periodic, the image is going to be something back here. So that remains your bounded portion. So it's no longer Bunge. Only when you are having a periodicity coming up like this, tending to infinity, this point goes here, comes up here, goes up here, and then comes back here. It becomes larger and larger, then it is possible. So, in fact, this is called the Baker domain. So, if it's a periodic domain, but not a Baker domain, then it will not have a Bunge set. Yeah, so this is the just your diagram that we have shown. It's basically just to show the diagram. The point is here, and then moves up here, then moves up here, then moves up here, and so on. So that's your Bunge set. 4, 1 by 16. So I have a subsequence which tends to 0, and a subsequence which tends to infinity. So a Bunge set will always have at least 2 subsequences, one converging, the other bounded. Means one tending to infinity, the other bounded.
One going to 0.
Not necessarily to 0, bounded. It is bounded.
Remain bounded.
It remains bounded.
That's what is more diversity.
The other one diverges to infinity. Now, interesting part, observe here, when you're talking about Julia set of Fn, you have some idea about the complex domain. Julia set of Fn is the same as Julia set of N. Padu set of Fn is the same as Padu set of N. But this does not hold true for a Bunge set because of this simple example. F of z is this, but the moment I take f of z square, it becomes a polynomial, and polynomial Bunge set is the empty set, whereas the Bunge set of 1 by z square is at the 2 regions. So the theory here is different from what we have for complex dynamics. So earlier we had divided C into 2 disjoint sets, but now there are 3 of them. So a lot of work on this has been going on. Now the question comes up, is there any pattern for them, for a Bunge set points? And the answer is no. Just to illustrate, very simple example, again 5 minutes.
30 minutes हो चुका है, 5 मिनट लेते
Okay. So just look at it. Suppose I had a pattern, say F3, F17, 7, 11, and go on, all bounded. And this 7, 14, 21, 28, tending to infinity. A pattern is there, 3 gap of 3 and a gap of 7 and so on. This is not possible. The simple reason is, let's look at say F21. It's just very simple example to illustrate a short, but general theory comes up. Let's say F21 is 36. Okay. Now observe what happens to F35, 15, and so on. Next is for 18 and so on. In fact, that's the formula that we have. 4 into 8, gap of 4, that's 32 plus 3, 35. So the 8th one that we have here would come in the top that is F30, this, so F35 would come in the top category. The top category would give you less than 32. Whereas 21, the next 28, 7, 35, it would also be in this category. And this category gives you 10 into infinity, that is more than 36. Because it's 10 into infinity, more than 36. So one is giving less than 36, the other is giving greater than 36, which is not possible. So it means it doesn't have that. They will crisscross. The idea is ultimately M, they will just come crisscross somewhere. So we cannot have that pattern. Of course, we may have some other pattern, but not the usual type of pattern. So there were other results that were obtained. Now, this was a result by Sixsmith that if f is a transcendental entire function, u is a Fatou component of f, and if u intersection Bungee set of f is non-empty, that means Bungee set intersects the Fatou set, then this result, if u intersects the Bungee set, that is your Fatou component, intersects the Bungee set, then your boundary of the Bungee set itself is your Julia set. So you can study again the Julia set using this concept. And again, a lot of work on this has been done, and in fact, I also obtained some results on this. Then, if f is transcendental entire function, Bungee set intersection Fatou set is non-empty, then Julia set of f is equal to the boundary of the Bungee set and the other terms. So, and in fact, it is known that if f and g are permuttable transcendental functions, and if Bungee set of f and Bungee set are non-empty closed subsets, then their Bungee sets are going to be equal. So that's the other result. There was a proof that I have got it because of shortage of time. I will not mention it, it's hardly one page. If the chairman allows.
Well, you just have 2 more minutes, even for the question and the answer thing, yeah, so.
I'll just mention that the idea is very simple. There is nothing special about it. No extra mathematics or other things. Just common logic that has been used to prove this result. Let f be transcendental function. If Z0 is in the Bungee set of composition, then G of Z0 is in the Bungee set of the reversion. The proof is simple. Suppose G of Z0 is not in the Bungee set, it means either it must tend to infinity or must be bounded. So either it is bounded or tends to infinity. If it is bounded, then I just take f on it. So f of the quantity, because it's bounded portion, so f of it by maximum modulus theorem, it is bounded by something. So m of af is bounded. This now becomes one portion. So we get f of g of n plus 1 less than or equal to ma. That means this becomes bounded, but for all n. But this is a contradiction because it was part of the Bungee set. So it's not right. Yes. So we get a contradiction. Similarly, the second one also, if I 2 holes, then once again, if since Z0 is in Bungee set, there is a sequence of this form. So G of the portion is again bounded, G maximum modulus. And so just interchange. So we get quantity m of bounded by this. That means the whole sequence is of this form is bounded contradictory. So again we get this. So just common analysis, nothing special. And the results of complex dynamics are basically complex analysis with little of juggling around to get the results. I think I'll stop at this stage. So I hope I'm in time.
Thank you. Yeah, you're exactly in time. Thank you so much. You're exactly in time, and if there are any questions, still you can do that.
Okay.
If there are any questions, then.
Extra time will be in his account then.
Exactly.
Thank you.
pleasure to do this. And very nice lecture, excellent. I just borrowed it. Because Amit Kumar. So next speaker is Professor Amit Kumar Verma from IIT Patna, and he'll be talking about on a class of real stable, non-standard finite difference methods. So using your laptop. So
No, this only, sir. This-
the last speaker is he came just now.
So, I'm audible. Good afternoon to all present. I would like to thank organizing committee for giving me this opportunity. So first of all, I'd like to thank the previous speaker. I was very much impressed by, at this age also, he has been very actively doing it. He cited one recent paper also, 2023, I think. So that is really motivating. I hope that I may also be able to maintain the same. Do we have this? Okay.
You just have to go close.
So-
Don't touch the board.
Okay, fine. So there are actually two terms you can see over there: L-stable and non-standard finite difference methods. So the talk will be based on basically some reviews, and that involves actually two names. So I have mentioned short biographies of two professors also in between, and I hope Professor Dutt must be knowing Professor Chawla. He has been alumni of IIT Delhi. Before I go ahead, actually, this topic I actually started learning from my wife when we started working together after marriage. So otherwise, mainly I work on theory of differential equations. So this is computational work, and so Dr. Lajja, she did PhD from Lucknow University only with Professor Kanti Pandey. And later, some of my students they did say Shireen worked on NSFD and non-standard finite difference methods, and Mukesh worked on he combined the non-standard finite difference scheme with Haar wavelets and tried to solve some complicated PDEs, nonlinear PDEs, including fractional PDEs and some integral equations also. Vamika is currently working on some NSFD problem. She worked with me 2 years. Now she is in Germany doing PhD from Hamburg University of Technology. So this is acknowledgement section. So as I said, there are basically two terms and there are two professors related to that work. So first one is Professor M. Chawla. So I have, basically this is the first paper which I read during my PhD. And most of my work I did refers this paper especially. On theoretical side, this is the only paper of Chawla, sir. But he has written several papers on computational aspect of these problems, and they are published in JAM journals, mainly. JAM Journal of Numerical Analysis, and BIT also. So he actually did his BSc and MSc from BU, and then he joined IIT Delhi in 1963. Then he did PhD later 5 years. So I don't know whether he did PhD from Delhi, IIT Delhi, or he did PhD from DU. That I could not, because this I have taken from INSA website. They have maintained his short biography. And then he became HOD also. He retired in 1994. Later he moved to Kuwait actually, and there he worked for long. And whatever work I'm going to refer is basically done from Kuwait. And this picture I got from Professor Meena Sai. She is currently heading this department, and I requested her because she is an IIT Delhi alumni, so she managed to give me. This is actually during convocation with his two students. He is standing. All of you know about finding out area under given curve. If it is not possible to integrate analytically, then you go for numerical solutions. So along this line, if you see the first one, trapezoidal rule is nothing but you approximate the function by polynomial of degree 1. Right. And then second one is Simpson's 1/3 rule, you approximate the function by polynomial of degree 2 parabola. Third one is the polynomial of degree 3. Surprisingly, the order of Simpson's 1/3 and 3/8 both are same, despite you go to higher degree. The order remains same. Okay, so the truncation error and the convergence, the derivations are very interesting, but they are very trivial and they are class materials. So basically, whatever I'll discuss, I'll be focusing around these three methods. And so if you can replace this function by, so you can approximate the function by a polynomial. You know that if you have a space of continuous functions, then you can approximate uniformly by polynomial of any degree depending on the accuracy you require. This is the basic idea. Then you can, this is complicated, this is simple, you can integrate and you will devise the formulas, various formulas of any degree. And again, this looks very simple problem, but in vector form, if you are able to solve these problems, this first problem, this is a test equation. When we devise a numerical method, we generally test it on this equation to study stability properties of the numerical method. It seems very simple, but sometimes, like if you have, say, some nonlinear PDE, say it is popularly known as Burgers equation, then basically what you do, you can try to discretize it by some finite difference methods, and then this problem you can write in terms of, say, vector form, right? It becomes a vector equation, and then you can apply this whatever method you develop here for this. And these methods, the previous methods I discussed, these three methods, they can be applied. You can integrate simply, and then they are nothing but integration of this function, numerical integrations. So regarding this, there are two definitions are very crucial because entire discussion will be moving around this. So for example, this linear test equation, you can easily solve, you get the solution, and when lambda is negative, real part of lambda, we can allow this lambda to be complex valued also, because when we deal with vector form, then matrices appear, and there you have complex eigenvalues also, they are allowed. So if t approaches to infinity, when real part of lambda is 0, this the solution decays. You can easily see that. Now if you have a one-step numerical method, one-step numerical method means this kind, right? You can apply it on this test equation, this method. So you get this kind of equation where this is the iteration function, right? And if the solutions for solutions to remain bounded, the modulus of this triple is equal to 1. Right? So this leads to a definition, which is called astability of a numerical method. So a numerical method is astable if this is satisfied for all z. That means if you see this in the complex domain, this condition is satisfied for the negative real part, entire half plane, negative on the other side of y-axis. Now a method is said to be, so your minimum, a method is said to be stable if the negative this other half of the plane, complex plane, for other half this is true. You can have a bigger region also, but minimum it should be there. What is L stability? L stability, if in addition to this A stability, if this occurs, then you say it is L stable. Now, why L stability is required? Because basically you are dealing with differential equations, and there are differential equations popularly known as stiff equations. What happens in stiff equations? The solution varies very quickly, rapidly in some time domain, and in some time domain it very slow. So the numerical method should be able to capture, any numerical method should be able to capture both. So if the method is L stable, then you can do it easily, and this first condition allows you to choose any step size. Because there the time domain where the solution changes very rapidly, there you have to take the step sizes very small. So now regarding this, I did not mention the name of, okay, so these are some examples like forward idle method, well-known method. It is conditionally stable. So it represents a circle with a center -1. So inside the disk it is stable. Backward Euler is, so this is not astable because for stability you need entire left half plane. So backward Euler is L stable as well as it is L stable also because it satisfies both conditions. For mod of phi z is less than equal to 1 and limit of phi z when z tends to minus infinity is 0. Then trapezoidal rule is A stable but not L stable. You can easily see that from this. Now, so regarding this, there is a famous, there are two celebrated papers written by Dahlquist. Now he wrote these two papers and he gave two barriers popularly known as first barrier, second barrier. First barrier says that no linear multi-step method of order greater than 2 can be stable. So if you try to devise a multi-step method whose order is greater than 2, order means order of convergence, then it cannot be astable. So researchers took this as a challenge and then try to devise the methods so that can be stable with a higher accuracy. Definitely, if it is a multi-step method, you cannot do it. So this is a very celebrated paper, and I have just taken some pictures for this. Like this paper is written by G. Vanner, published in Bit Numerical Mathematics 2006. He only talks about his paper, and then there are some pictures like in this paper. This is the slides used by Dahlquist during slides of the author around 1980. His notes that he prepared for it, and this is also from his letter. And these diagrams in relation to stability, I don't know how to explain it, but these are his diagrams which he used during the presentations. Now, coming back to this development, so basically, if you have a linear multi-step method, then if you try to increase accuracy more than 2, then it cannot be stable. So researchers try to devise methods of higher order accuracy which can be stable. And what they did actually, so these are the initial results by these two people, but there are some weaknesses Like during those days, there was no computer algebra. The software was only maybe Fortran was there. I don't know. Fortran, whatever languages were there. So, but nowadays we have Mathematica and Python is there, so you can compute all these very easily. So this computation, they use this actually during the computation, which was difficult. So Usmani and Agrawal, they derived a stable version of trapezoidal rule. Trapezoidal rule is yes. So they this is the paper. So they extended the trapezoidal A-stable extended trapezoidal rule for the integration of following differential equation. And what they did actually, very cleverly, what they did, they added. This is actually the formula alpha and alpha one. If you take as half, you get that formula. So they added one more term, and then this term they again compute in terms of the Zn and Zn plus one. Right, very clearly, and then you compute the truncation error, and then you get some equations in powers of h, and you equate it to 0 to get the required method. So based on this, they got a stable method, which is not L stable, but error of accuracy is increased. How is it possible? Because this method, this seems to be a multi-step method, but actually, because n plus 2 is again depending on n and n plus 1, so it becomes one-step method. That means finally, n plus 1 is depending on only n. This is very clever. They try to work on. Cleverly, they try to work on. Now, further this, he extended the method for so he further extended it, and the method developed by Smani and Graham, that was not L stable, so it is not applicable for state equations. So he derived it, and he could derive L stable method. So what he did, so he did it with this. This is wrong, 1985. So he took less equation actually. So you have one parameter in your hand that so that you can play with it. So finally, this he derived a family of methods which were not only A stable but L stable also. That was the advantage. Right. Then they said that if you want to further increase the accuracy, then one-step method is not sufficient. They went for two-step methods. Right. Jacques with his colleague. And again, what they did is they added one more term, and then this term they again define in terms of the remaining n plus 1 and n plus 2, and derived the method. This basic idea. Now, why is moving? Okay. Now, after this, here comes Professor Chawla. What he said, no, it is possible to increase accuracy further with the one-point method, right? And he devised it. What he did, he defined this n plus 3 in terms of n plus 2, and n plus 2 again in terms of n plus 1. So finally, it becomes one-step method, and again, the idea is to reduce the number of equations, so you have more free variables you can choose. So you derive two-parameter family of numerical methods, right, in this paper. And they are all modifying the trapezoidal rule actually. They are all modifying. Now, again, what they did is they generalized the work of Usmani and Agarwal, and they increase the accuracy, and the maximum order can be for the maximum order that they achieve is they proved it. this paper is very crucial, right? This is Simpson's 1/3 rule. And they again, what is the trick? This is a multi-step method, you see. So what they did to make it two-step, this n plus 1, 1th value, they again defined in terms of previous, the other n and n plus 2. So it becomes one-step method. And they defined double stride means, basically double stride means you are using say xn plus 1 and xn plus 2. So double stride means you are basically focusing on this h and h2h. That is why it is called double stride. So they again gave L-stable methods, but this time instead of using trapezoidal, they used Simpson's 1/3. In another paper, he derived a class of trapezoidal formulas. Idea is very simple, right? One more term is added over here with alpha variable, which they can define whatever, whatever they wish, and then they define the family of problems which are L-stable and A-stable depending on the value of alpha. Right. So what is the motive here? Increase accuracy, and you find out A-stable method which is also L-stable. Right? And they have convection diffusion equation, as I said, these kind of equations. They have taken a maybe linear version of this. This is for the application purpose. They applied it on PDEs. As I said, you can write in this form, and then you apply finite difference here. Then it becomes a equation of this kind, which you can solve by these methods. So now here comes motivated us, and what we did that in this paper, Chawla yn plus 2 equals to yn plus h by 3 and plus time. So this function fn plus 1 cap means fx cap, and this yn plus 1 they compute by taking the average of, say, for example, take this. So yn plus 1 you can take the average of what? The values at simple interpolation actually. But this averaging is not necessarily this. Maybe you can use 3, 4, and 7 also. So this averaging they have done very cleverly, and then they Simpson's 1/3 rule, and then they applied it on some nonlinear PDEs, and they have shown that Klein-Nicolson scheme, very popular scheme to solve PDEs, is better than this, because when time step is large, Klein-Nicolson method gives oscillations actually, but because this method is L-stable, it does not give you oscillations. Here the order is 3, Simpson's method order is 4, but when you convert into L-stable, it becomes 3rd order, but it gives you L-stability, which has more advantage. Now, there is one more thing, and you use this that is called backward Euler formula. This backward Euler formula has shown it is L-stable. So here you cleverly do this and then choose one of the say yn plus 2 and replace it by this. So it induces L-stability because it is L-stable. So this is a very clever selection of. Now based on this, what we did when we got to know about it, we tried to do it for Simpson 3/8, and we tried to see what will happen. But so Simpson 3/8, there is one more term. So yn you can write. So you will have one more term for yn xn plus 3. So yn plus 3 equals to yn plus 3h by 8. Then you will be getting fn plus 3 times fn plus 1 plus 3 times fn plus 2 plus fn plus 3. Right.
So you have to, like, whatever you have done here for this, you have to do it for these two. And average it in terms of these two. Yes.
minus only. वो अगर 10 मिनट वो क्वेश्चन आंसर वाले दे देंगे तो मैं कंप्लीट कर लूंगा.
5 plus 5, yeah. 5 minutes for question answer.
Okay.
Essentially, it has been
Fine. So
We extended it for Simpson's theory. Finally, conclusion is that whatever we tried to find out a different method, but Simpson's 3/8 still gives the same problem, same formula, right? What is the advantage of this? You can see that here this exact for this Burger's equation, very popular equation. It's called 1D analog of Navier-Stokes equation. So the exact solution also it is in terms of Fourier series. It oscillates for small values of viscosity. But our solution that is numerical because of it is stable. It gives you better results. It is not oscillating. Again, I'm showing it here for various graphs that even if you decrease coefficient of viscosity, still you are able to maintain the profile. That is not possible. Very difficult.
Yeah, I went.
And again, we have also shown that Bragg-Nicholson method oscillates, but this is not oscillating. Similar to the other observation which Professor Chawla did. Now here again, we went for further generalization. We increase the degree of the polynomial. What is the degree of the polynomial here? It was, in case of this, it is P3. So we go to P4. So this one is for P4. But initially when we submitted it, we missed a point and this paper was rejected from one of the good journals and we had to modify it. So basically this method is not astable because its stability region is not the entire left half plane. There are some points which create problem because the polynomial is a rational function. This pi z is a rational function. So polynomial has zeros which are on the left. So that creates problem. So it is not astable, but still it is unstable. So because it is unstable, so still it gives you advantages when you deal with stiff problems. So then further we generalized it for one more higher degree. But here there is a slight innovation that we used non-standard finite difference methods. So very recently, this is I think published in 2020. Very recently, last year, we did it for any degree. You did it for like we have given a formula. You put you change the value of this n. You can take any n. You can derive the formula. Yes, we discussed it. Algorithm is given, and this is again my wife is there. The paper. Because I started learning from her initially. So now what is NSFD? So I plan to do this also. So let's quickly, I'll just tell you. So R.E. Meekins is the main person behind it. He is a professor of, he is one of the editors in Journal of Differential Equation and Difference Equation, published from Taylor Francis. And he is a professor of physics at Atlanta University. He is the highest grade point. He got highest grade point from his like in the university history. And his thesis is basically branch points in the complex. You require good understanding of complex analysis to deal with the stability. Actually. Without that, you can't do it. And I think it is because of this he could devise this method. So he has several solo author papers and books he has written. What happens actually, suppose this is a decay equation, if you apply it, see, these methods are very popular. So all these methods, they require some condition, then only the solution will converge. Only this backward arrow method is convergent for all because it is unstable. So whatever finite difference method you try to derive, there are problems actually. So this is the motive. So in this regard, R.B. Pott, he gave two papers. This is a differential equation, d by dx, d by dt, whatever. This is a difference operator. He said that if you can devise a